Hey guys, welcome back. Hopefully Tensor Calculus is going so far so good. It's been mostly a review. Just a few things we did last time were a little bit new. So today we're really going to get into some new material. It's going to be familiar in that you've seen a lot of these things before, but now we just have a new perspective on what we're doing with them. So today is called Curvilinear Coordinates. It's chapter 7 in your first book that you have, so chapter 7. It's all about curvilinear coordinates. And so really the idea is, suppose that the rectangular coordinates x, y, and z are functions of other coordinates, and we'll call those u1, u2, and u3. And we said if we just have like a coordinate system, then we're just going to arbitrarily put the index up for no real reason. We just, for its coordinates, we always stick the index up for some reason. We don't have like a good reason to explain that right now, but for coordinates we're always going to put like the index on the top. So basically that would mean that x is a function of u1, u2, u3, y is a function of u1, u2, u3, and z is a function of u1, u2, u3. So all of our coordinates x, y, and z are functions of these other coordinates. I mean, you could think of these as like spherical coordinates or cylindrical coordinates, or so many different coordinate systems. So then, so if it's invertible, if it's possible, and it usually is, and if it's possible to represent the inverse transformation, then we could say that u1 is a function of x, y, and z, u2 is a function of x, y, and z, and u3 is a function of x, y, and z. So that's like saying, okay, for spherical coordinates, x is equal to rho cosine theta sine phi. Y is equal to rho sine theta sine phi. So basically, like, your x, y, and z are your Cartesian coordinates, rho, theta, phi are your spherical coordinates. Well, there's a way to say rho, that could be like u1, rho would be equal to the square root of x squared plus y squared plus z squared. So it's like a way to get the other coordinate if you know the Cartesian coordinates, and vice versa. So that's just all we're saying here, is like, suppose that these two exist, like there's a transformation, the original transformation from curvilinear coordinates to Cartesian coordinates, and then there's also an inverse transformation from Cartesian to what we call now curvilinear coordinates. So in general, we call u1, u2, u3 curvilinear coordinates. So I call them curvilinear coordinates. They may or may not actually be curved, but most of the time they are curved, and we would call them curvilinear coordinates. Now if we just work with two variables, x and y, we can look at a nice easy example here. So for example, we could have polar coordinates. So polar coordinates in 2D, normally we would say x equals r cosine theta and y equals r sine theta. But if we want to use the notation u1 and u2, we can let u1 equal r and we can let u2 equal theta. So then we would have the Cartesian coordinates x equals u1 cosine theta, y equals u1 sine theta. So that would be, oh, sorry, not theta. We're not using theta, we're using u2. So that would be cosine u2 and sine u2. So that's just an example of curvilinear coordinates. If we draw out the coordinate system on a graph, we know that if we have xy coordinates like this, then our curvilinear coordinate system, we could say, okay, this is like r equals 0, this is r equals 1, and this is like r equals 2, this is like r equals 3. Now theta equals 0 is right here. So this is theta equals 0. Theta equals pi over 4. Theta equals pi over 2. Theta equals 3 pi over 4. Theta equals pi. So it's just the same two-dimensional space. We're using different coordinates to describe it though. So this point right here would be the point r equals 3, theta equals pi over 4. Whereas in xy coordinates, you know, it'd be whatever, 3 cosine theta and 3 sine theta for the xy values. Kind of like we did previously with the rotated Cartesian coordinate system. It's just now we have a curvilinear coordinate system because the lines of the coordinates are curved. We have circles for constant values of r. R is just the radius from the origin. So we know that u1 squared, or u1 would be square root of x squared plus y squared, and u2 would be arctan y over x plus pi if needed. So we could invert that transformation and get the u1 and u2 in terms of x and y, just like we were talking about in our setup. Of course, we're only doing this for 2 dimensions right now. We could switch over and do it for 3 dimensions. So another example would be spherical coordinates. So spherical coordinates, what do we know? We know x is equal to rho cosine theta sine phi. Y is equal to rho sine theta sine phi. Z is rho cosine phi. Of course, you have to be careful. Some books or some discussions will swap theta and phi, but I use theta as the rotation around the z-axis and phi is the angle off of the z-axis, the azimuthal angle, and theta is the polar angle. You can swap those, just have to keep them straight in your brain. I think our book actually has them swapped, but it doesn't matter. So you can let u1 be rho basically, and u2 be theta, and u3 be phi. So you could actually just write this in the same way that we had earlier. We could say x equals u1 cosine u2 sine u3, y equals u1 sine u2 sine u3, and z equals u1 cosine u3. So that's kind of like our setup that we would have. Of course, normally u1 theta is between 0 and 2 pi. At least that's the way that I normally set it up. And then phi, the azimuthal angle, is between 0 and pi. So that's u3 between 0 and pi. And that can access any point in the 3-dimensional space. So you extend the radius, the rho, from the origin out to whatever point. You rotate around the z-axis, and then you rotate down from the z-axis to access any point in the three-dimensional space, and that would be a coordinate system in 3 dimensions. That's curvilinear. So curvilinear coordinates in 3-dimensional space. You could think of like any point in the 3-dimensional space as being somewhere on a sphere. So that sphere right here, this point, some distance away from the origin, rho or u1, some angle off of the positive z-axis, theta or u2, and then some angle down from the positive z-axis, call it u3 or phi. So that's the coordinate system there. So the spherical coordinate system. Any point in the 3-dimensional space is, you could say it's somewhere on a sphere. Now, what are we going to do? We're basically wanting to take the ideas that we talked about already and try to extend them to curvilinear coordinate systems. We've talked about the fact of tangent vectors, we talked about gradients, we talked about basis a little bit. So recall a few things here. Any vector A can be written as, we'll call it A1 I hat plus A2 j hat plus A3 k hat. So we call I, j, k that set a basis for R3, because any vector in 3-dimensional space can be represented as a combination of these 3 vectors. Then we call that set of vectors a basis for the space. Also, they're unit vectors. That's not like extremely important for a basis, but some people like it to be a unit vector. So really all we got to do to define a basis in a coordinate system is either look at some tangent vectors or look at some gradients. So let R be equal to the position vector xi plus yj plus zk. So it's going to be the position vector. So let R be the position vector of a point, we'll call it P, in Cartesian coordinates. So we're using Cartesian coordinates to describe the location of this point. So then R is really a function of x, y, and z, but x, y, and z we can assume are functions of the curvilinear coordinates. So it's really a function of u1, u2, u3, since x, y, and z really depend on u1, u2, u3. So now note that partial r, partial u1 is tangent to u1 at P. So I'm basically differentiating the radial vector with respect to the first curvilinear coordinate, or in the direction of that curvilinear coordinate. So this is going to be tangent to the first coordinate, basically. If you could think of this as like taking derivative with respect to x, then you're looking at the tangent vector in the x direction. So now, likewise, partial r, partial u2 is tangent to u2 at point P, and partial r, partial u3 is tangent to the u3 axis at point P. Now we let E1 be equal to partial R partial U1 over magnitude partial R partial U1, and E2 and E3 be defined similarly we call these the unit tangent vectors. So we call these the unit tangent vectors. Of the coordinate system. So these vectors are tangent to the directions or the coordinates u1, u2, u3. So we'll go through an example to see what it looks like for maybe polar coordinates. We'll go through, we'll calculate these vectors. But yeah, this is just a basic definition, basically. So definition, that's really what this is. Defining these unit tangent vectors. Now they don't have to be unit vectors. We would have a basis regardless. But if you think about this, if you say, okay, what if we didn't use like curvilinear coordinates here? What if these were just x, y, and z? Partial r, partial x would just be I hat, right? Like partial r, partial x would just be I hat. So that would be in the direction of I hat, that would be tangent to the x direction. Partial r, partial y would be j hat. So it'd be tangent to the y direction. And then partial r, partial z would be k hat. So if you just use Cartesian right here instead of general u1, u2, u3, you would get I, j, and k basically. So that's what we're doing, is just generalizing the idea of a basis in Cartesian to a basis in any coordinate system. So also recall that the gradient of f is perpendicular. So, or perpendicular to f at any point on f. What we're going to do now is we're going to draw a coordinate system and start to define some what we normally would say would be planes, coordinate planes. We're going to define coordinate surfaces. So we'll think about this in x, y, and z. So x, y, and z. This plane right here is y equals 0. The y equals 0 plane. So y equals 0 would be this plane right here. And then this would be the plane x equals 0. So the x equals 0 coordinate plane, and then the xy plane we know is this plane. It's the z equals 0 plane. It's just the coordinate planes, if you will. Now, what we can do is we could say, okay, well, in a curvilinear coordinate system, we'll just draw arbitrary curvilinear coordinates, u1, u2, and u3. So u1, u2, u3. So now, like u1 equals a constant would be something like this, u1 equals a constant. It'd be some surface. Same thing here, u2 equals a constant. Would be some surface. And then u3 equals a constant would be some surface. So u1 equals a constant is some surface. u2 equals a constant is some surface. And u3 equals a constant is some surface. Now what we're going to do is take the gradient of those surfaces. So gradient of u1 is perpendicular to u1. So that would be something like that. Gradient of u1. And the same thing here, take the gradient of u2, maybe something like that, gradient of u2, and then gradient u3 at different points. So gradient of u1 is perpendicular to u1, gradient of u2 is perpendicular to u2, and gradient of u3 is perpendicular to u3. So now what we can do is definition. What we can do is we can define. So now we define call it capital E vector 1 as gradient of u1 over magnitude gradient u1. Capital E2 is gradient u2 over magnitude gradient u2. And capital E3 is equal to magnitude, or gradient u3 over magnitude gradient u3. So this is just a different, what we call, set of basis vectors. So the set E1, E2, E3 is a different basis, or I should say not different, it could be the same, but is another basis for the space. All of these vectors, all vectors in the space could be represented as some combination of these three vectors. So actually, in general, we have at least two bases for our space. E1 lowercase, E2, E3. Those were just the tangent vectors. Well, now these are the orthogonal vectors to the surfaces of constant coordinate values. Capital E1, capital E2, capital E3. So this is the tangent basis, and this is the orthogonal, like the orthogonal direction to the tangent surfaces, or sorry, to the constant surfaces, the surfaces of constant value. So for Cartesian, example, for Cartesian 3D space, what would we have? The lowercase e1, so that's the x direction, that's the y direction, that's the z direction. Lowercase e1 says go in the radial direction, differentiate this way, we get e1. So r equals xi plus yj plus zk. Take the radial vector, differentiate that radial vector with respect to x. We would just get I hat. And that would tell us E1 would just be I hat. Partial R, partial Y would just be J hat. So E2 would just be J hat. If I divide it by 1, it doesn't change the vector. And then partial R, partial Z would be K hat. That would be E3. So E3 is K hat. So that's your E1, E2, and E3 vectors. So that's your, what we call the tangent basis, or the basis of tangent vectors, tangent to the radial vector. Now, what is this gradient nonsense? Like, how do we calculate those? Well, this would be x equals 0, this plane x equals 0, x equals a constant. What is orthogonal to x equals a constant? Well, that's E1, or gradient of x. So gradient of x would just be the vector 1, 0, 0. So it's actually also I hat. So gradient of x is actually also I hat. So capital E1 is also I hat. Gradient of y. Literally take the gradient, use the definition. Partial derivatives with respect to x, y, and z go in the x, y, z components. You get j hat. We did this on the board on our second day, and this is j hat. Gradient of z would be k hat. So that'd be E3 equals k hat. So the bases here are actually the same. It's the same set of basis vectors. So this is gradient of z. This is gradient of y. Like, this is y equals a constant. This is z equals a constant. So that's our different basis vectors. This is like capital E1. This is capital E2. This is capital E3. So we actually always have two set of basis vectors for any three-dimensional space. And that's a really cool thing to look at. Let's look at a different coordinate system that we talked about. So example, let's look at Cartesian coordinates in 2D. So consider 2D Cartesian and a general linearly transformed set of coordinates. Linearly transformed set of coordinates. So we talked about linear transformations already. So Cartesian would be something like this. It's x, y. And some general linearly transformed would be something like this. We could say x prime and maybe y prime. So these could be your general linearly transformed coordinate system, x prime, y prime. Now, E1, lowercase e1, is going to go tangent to x1. So that's lowercase e1. And then lowercase e2 is going to go this way. Now, what about capital E1? It's going to be perpendicular to this line, so that's going to be capital E1. And this is going to be capital E2. So in this case, the vectors are not the same. In this case, so here, the set E1, comma E2, lowercase, is not equal to the set capital E1, comma capital E2. So the question really is, when do these two sets of basis vectors, or when are these two bases the same? So question, when are these sets of EI lowercase equal to the set of EI uppercase? And the answer is when the coordinate system is orthogonal. That means your basis vectors are orthogonal to each other. meaning perpendicular. Well, we can see here E1 and E2 lowercase are definitely not orthogonal. They're not at a right angle to each other. The same thing here, capital E1, capital E2 are not at a right angle to each other. But if you look at Cartesian coordinates, I and j, those are orthogonal, or even 3 dimensions, I, j, k, those are all orthogonal. So we can find out if the system's orthogonal or not by calculating these basis vectors and then taking their dot products. So that's when these two sets of basis vectors will be the same as when the coordinate system is orthogonal. If they're not orthogonal, if the basis vectors are not orthogonal to each other, then these two sets of basis vectors, lowercase e, I, and capital EI, will not be the same. So let's look at these basis vectors in polar coordinates. So example, compute E1, E2 lowercase, and capital E1, capital E2 uppercase for polar coordinates. So for polar coordinates. So for example, going to look at these in polar coordinates. So what do we do in polar coordinates? Well, what we do is we start off with solution here is x equals u1 cosine theta, cosine u2, and y equals u1 sine u2. Now, r, we said, was xi plus yj, which is going to be u1 cosine u2 I plus u1 sine u2j. Now, E1 is the derivative of r with respect to the first component. So partial r, partial u1 is equal to, so differentiate this with respect to u1. We just get cosine u2 I hat plus sine of u2 j hat. Again, this is like a u2 as a variable, not u squared. Right? u2 is a component and a coordinate. So basically theta. Now, what's the magnitude of this? So magnitude of partial r, partial u1 is equal to square root of cosine squared u2 plus sine squared u2, which is 1. So that means our first basis vector, E1, is equal to cosine u2 I hat plus sine u2 j hat. So in Cartesian, this is kind of what it would look like. In the new coordinate system, it's just its own unit vector. So let's look at what happens. Like E1 is actually a function of u2. So what is E1 of 0? Well, that'd be 1 I hat plus 0 j hat. So if we plot that in a two-dimensional space, E1 of 0 looks like this. So that's E1 of 0, lowercase. Now what's E1 of, I don't know, pi over 4? E1 of pi over 4 is equal to square root of 2 over 2 I plus square root of 2 over 2 j. So that would be E1 of pi over 4. And you got the idea, it's always tangent to the radial direction. So E1 of pi over 2, E1 of pi, etc. So that's the idea. That's our radial basis vectors for polar coordinates. So that's our new basis vector. We could basically forget about I, j, and k and just think of these vectors now as going around the two-dimensional space and write everything in terms of these vectors. So we're just so accustomed to I, j, and k. This is like a new vector that's kind of independent of I, j, and k. We just use Cartesian to derive what it looks like. But on its own, it could be, placed in the space, you could use it and another one that we're about to derive, E2, and represent everything in the space, every vector in the space as a combination of these vectors. So let's look at, let's go back up here, take our position vector and differentiate it with respect to U2. So call that R is equal to U1 cosine U2 I plus U1 cosine U2 sine U2J, sorry. So U1 sine U2J. Now partial R, right lowercase, partial R partial U2 equal to negative U1 sine U2 I plus U1 cosine U2J. And now what is the magnitude of that vector? Magnitude partial R partial U2 equal to the square root of, that's going to be U1 squared sine squared U2 plus U1 squared cosine squared U2. Well, that's just going to be square root of U1 squared, which is U1. So now E2, the second basis vector in polar coordinates, is going to be divide, let's see, it's partial R partial U2 over magnitude partial R partial U2, which is going to be, let's see, that's just negative sine U2 I hat plus cosine U2 J hat. So that is a function of U2 as well. So E2 is also a function of U2. So let's plot different values of U2. So E2 of 0 be equal to 0I plus J hat. So if we plot the E2 vectors, the unit vector, but it's at theta equals 0, it points up, so that's E2 at theta equals 0. What about E2 of pi over 4? E2 of pi over 4 equal to negative square root of 2 over 2I plus square root of 2 over 2J. So it points negative square root of 2 over 2I positive square root of 2 over 2J. So E2 of pi over 4. So it's just that tangent vector that we talked about previously to the circle. So it's actually tangent to the circle. So this would be E2 of pi over 2. This would be E2 3 pi over 4. This would be E2 of pi. So the only weird thing here really is the fact that we have basis vectors that change direction depending on where you are in the space in relationship to the origin. So that's the only weird thing going on. The idea is still the same. These are tangent to your coordinates. Theta goes around, R goes out from the origin. So if you look at these two, basically you have E1 there, you have E2 here. And we can see that these are orthogonal. So your basis vectors and polar coordinates are orthogonal to each other. So E2 of pi is pointing down. You can go through and verify this when you calculate E2 of pi. Now you could completely forget about Cartesian coordinates and just work with these basis vectors on their own terms, which is the idea of tensor calculus, to kind of forget about any one particular coordinate system and work with, what you have on its own terms. So that's a good discussion right there. We basically derived these things in Cartesian coordinates. Now let's derive capital E1, E2 in Cartesian coordinates. So find capital E1 and capital E2. So U1, let's look at it. U1 equals square root of x squared plus y squared, right? And we set that equal to a constant. So then what is the gradient of this function, square root of x squared plus y squared? The gradient of that function is going to be 2x over 2 square roots of x squared plus y squared I hat plus 2y over 2 square root of x squared plus y squared j hat. Right, this is basically r equals square root of x squared plus y squared, and then taking the gradient of the surface because I set the first coordinate u1 equal to a constant. So take the gradient of this function, which is this vector here, which is x over, we'll call it magnitude of r, I plus y over magnitude of j, or sorry, magnitude of r, j. So that is our E1 vector. And the gradient, the magnitude of the gradient, so this is gradient of U1 basically. And magnitude of gradient of U1 is 1 over r times magnitude of r, which is 1 over r times r, which is 1, if we're letting little r equal magnitude of r, which is square root of x squared plus y squared. So then, capital E1 is equal to x over r I plus y over r j. And if you were to plot that in the two-dimensional space, we'd see, okay, at 1, 0, this would be a vector that's 1, 0. So that's capital E1 of 1, 0, which would be the vector I hat. At the vector 1, 1 points this way. That's capital E1 of 1, 1. So it's the same. It depends on where you are in the space. So capital E1 of 0, 1, etc. And these are the same as the lowercase e1s that we talked about earlier. So because it's an orthogonal coordinate system. Now let's calculate E2. So it's a little bit more complicated because U2, we know there's arctan y over x. So gradient of, if we set that equal to a constant, gradient of U2 is going to be a little more complicated. We have to differentiate this thing with respect to x. So that's going to be 1 over 1 plus y over x squared times derivative of y over x with respect to x is negative y over x squared I. So that's the x component of the gradient. Plus, pretty much the same thing, almost the same thing, 1 over 1 plus y over x squared times 1 over x. Right, the chain rule, j. So that's the gradient of this function arctan y over x. So now distribute that, calculate the gradient of U2, or just simplify the gradient. We're going to get negative y over x squared plus y squared. I plus 1 over, let's see, x plus y squared over x j. And I think what I want to do to the j component is just multiply top and bottom by x, just to make it a little bit better to look at. So this is really negative y over r squared I plus x over r squared j. Again, if you plot those, it'll be similar. It'll actually be the same thing as what we had earlier for lowercase e2. So at maybe 0, 1, this is the vector, or at 1, 0, this is the vector 0, 1. This is capital E2, capital E2, capital E2. You can go through and plot those points at different xy locations. You get these capital E2 vectors at different xy values. Let's see, the magnitude here, I don't think it's the same, so actually it should be capital E2 going to be gradient of U2 over magnitude gradient of U2. And magnitude gradient would be, let's see, 1 over r squared times r, which would be 1 over r. So I need to actually multiply this thing by r, which is going to be negative y over r I plus x over r j. And that's our E2 vector, our capital E2 vector. Again, if we plot it over here at different xy values, we'll see that the capital E2 vector looks like this. So it changes throughout the space, just like it did before, except we just use a different method to derive it. And they're the same because this is an orthogonal coordinate system. The E1 and E2 vectors are orthogonal to each other in both ways. Like no matter if you derive it using the tangent vector or the gradient, you get the same vector because it's an orthogonal coordinate system. Now I know that's a lot to take in. We're going to stop right here. We're going to process a little bit of this, work through some of the details. If you didn't get it, slow it down, rewind it, just do whatever you got to do to take it in. But I know you guys can do it. So if you have any questions, of course, just post in the comments, or if you want to hit me up on Discord or whatever, that's fine too. That's good. So we'll just have a discussion, do whatever you need to do. But take some time with this one, really soak it in. It's a good one. It's really important for a launching pad for where we're going to go when we get to tensors.